Good morning, everyone. I am here today to talk to you about the subject of my presentation, which is the structural and elastic properties of ternary galide magnesium cobalt digalide component. The plan is given as follows. Firstly, we will start by introduction. Next, we will look at the calculation method. Then we will talk at our result and discussion about the structural and elastic property. Finally, we will finish our presentation by conclusion. The major goals of the solid-state chemists have been to achieve a comprehensive understanding of the interrelationship among stoichiometry, crystal structure, physical properties, and the chemical structure of the solid-state component. Based on fundamental understanding of this relationship, we can create a galide magnesium cobalt digalide materials which show precisely designed crystal structure with the property specifically tuned for certain purpose. Such questions include: how can we understand the driving forces of the atomic arrangement in a complex solid that exhibit interesting chemical and physical property? How do different elements distribute themselves in a solid state structure? Can we develop a chemical understanding to predict the effect of valence electron concentration on the structure ordering of system by both experimental and theoretical means? Although these issues are relevant to various component classes, gallium components are especially interesting and well suited for joint experimental and theoretical effort. For a gallium magnesium cobalt, the gallium component, the question listed above are difficult to answer, since many of the constituent atoms simply do not crystallize in the same manner as in their separate elemental structure. To understanding the nature of this component is still not complete, mainly due to the strong bias imposed by application research and to non-sufficient comprehension about their chemical binding. Moreover, it must be realized that attempts to find a causal link between propriety and the chemical binding in this class of inorganic substance are often frustrated by the lack of the reliable information on binding and properties and therefore on their relationship. The corresponding first principle calculations were performed using cascade code, based on the density functional theory DFT, within the GGA approximation by the PBO Sol exchange correlation function. The Coulomb interaction between a valence electron and the ionic were described, including the van der Waals ultrasonic pseudo-potential. The Briançon integration is performed using a specific point set, which was considered with a 3-2-2 K mesh for all structural and elastic properties, and the plane wave cutoff energy is 280 electron volt was respected through the calculation to estimate the number of the plane wave. The elastic constant were determined by applying a set of a given homogeneous deformation with a finite value and calculating the resulting stress with respect to optimizing the internal atomic freedom. In the next slide, we will see our result and discussion. As shown in figure 1, the crystal structure of magnesium cobalt digalide was solved by direct method and refined into space group as P21C and P21N. The obtained structural parameters of this component at the ground state under pressure are listed in table 1 together with other available experimental data. Our results at 0 pressure in good agreement with the experimental values. This ensures the reliability of our study. The observed band length of the different atoms of this component can be successfully estimated based on previous experimental data under pressure. In order to study mechanical property of this component, we have calculated the elastic parameters such as the elastic constant, bulk modulus, shear modulus, Young modulus, and the Poisson ratio, and all directional anisotropy from obtained elastic constant according to the Voigt-Roos-Hull approximation. Let us discuss the trend in the elastic parameter for our component. The calculated results of elastic constant under pressure are illustrated in table 2. It can be seen that the value of C12 is smaller than the average of C11 and C22. C13 is smaller than the average of C11 and C33, and C23 is smaller than the average of C22 and C33. This means that the resistance to the applied stress are higher in the direction 100 than in the direction 001. This means that the structure along the R-axis is stiffer and the R-axis is more compressible than the C-axis. Also, the calculated values of C33 is less than that of C11, which represent the lowest of lattice interaction along C crystallographic axis. Similarly, the calculated value of C44 is greater to C66, which means that the soft sharing transformation is difficult about 100 plane than in 001 plane. Within the pressure considered, the elastic constant obeys the stability criteria, indicating that this component is mechanically stable under pressure. The calculated of the bulk modulus, Young modulus, Poisson ratio, hardness, and shear modulus, and anisotropy factor under pressure are shown in Table 3. Once the single crystal elastic constant are computed, the related properties of polycrystalline can be evaluated. From this table, it's seen that the bulk modulus is higher than shear modulus, which indicates that the parameter limiting the stability of monoclinic structure is the shear modulus. Also, it's obvious that the value of the ratio bulk modulus shear modulus is about 0.61 at 0 gigapascal, which indicates that this component has a brighter future. For 10 gigapascal, the values of this parameter are greater than 0.47. That is to say, at higher pressure, a magnesium cobalt galide possesses a better ductility. Since the calculated Poisson ratio of this component is about 0.24 at 0 gigapascal, which means that this component is brittle and the contribution of interatomic bending within this component are ionic. The calculated result of hardness for this component is also listed in this table. It can be seen that the estimated value of the hardness at 0 gigapascal and 10 gigapascal is about 9.65 and 9.37 gigapascal respectively. Thereby, the low hardness of this crystal can be referred to as the low density of crystal structure. Clearly, this component has a small hardness and their hardness is less than 14 gigapascal. The universal elastic anisotropy index is an appropriate measure of the degree of anisotropy. It's clear that the value of this parameter is about 0.42, indicating that this component is a highly anisotropy under pressure. The elastic anisotropy behavior more directly and effectively we summarize of the elastic property of magnesium cobalt gallium crystal, the maximum and the minimal values of Young modulus, shear modulus, and the directional Poisson ratio in table 4. As shown in this table, Young modulus research the maximum along 010 direction at about 144.72 gigapascal and reduce it to the minimum from the 110 plane direction at about 97.04 gigapascal. This gives the anisotropy of the elastic modulus at about 1.4. The calculation gives the maximum shear modulus is about 78.77 gigapascal along 001 direction, with shear stress exerted along the 101 direction, while the minimum shear modulus is about 40.14 gigapascal along the 100 direction with a shear stress along the 011 direction. The corresponding anisotropy of shear modulus is about 1.94. Further, the Poisson ratio range from 0.01 to 0.87, implying that this material is brittle and anisotropic in nature in response to stretch or compression. Under pressure, the anisotropy factor is higher than zero pressure. The given anisotropy of the elastic modulus for Young shear modulus are about 1.42 and 2.03 respectively. In the next two slides, we outline the three-dimensional plot of Young modulus of this component as well as a two-dimensional projection in XY, XZ, and YZ plan of Poisson ratio, Young modulus, and shear modulus at different pressure. From the 3D spherical contour plot is accompanied with the 2D projection in different plan. It's found that the Young modulus exhibits clearly anisotropy, and the greater the pressure, the more obvious the anisotropy, because its spatial shapes are kept closed to the ideal isotropic sphere. Further on, it's shown that in axis direction, our component has the smallest values of Young modulus, and in a transverse direction, the greater values. This is also confirmed by the 2D plots. Yet, the shear modulus show stronger directional anisotropy, so we can say that this mechanical anisotropy is related with the crystal symmetry. At a top of the 2D projection in a different plan of the Poisson ratio show that this component has a great amount of anisotropy. After this easy interpretation, we explain that the shear modulus and the Poisson ratio depend highly on the direction. Our material predicts to have a greater anisotropy character under pressure in Young modulus, shear modulus, and the Poisson ratio. This indicated by the shape of the surface in this fix. However, the surface contour of this structure at 10 gigapascal is close to an ellipsoid, which implies that Young modulus has a weaker anisotropy than other pressure. Further, the shapes of the surface for shear and the Poisson ratio are far from the spherical shape and exhibit a very obvious anisotropy. So, this fix shows the clear anisotropy of Young modulus, shear modulus, Poisson ratio, and the greater the pressure, the more obvious the anisotropy. Finally, we can conclude that our component, magnesium cobalt, the gallium structure is mechanically stable at 0 and 10 pressure. The anisotropy property of this structure were visually illustrated and discussed by analyzing the anisotropy and directional Young modulus, shear modulus, Poisson ratio, with suggesting that this component is a relatively anisotropic material and the pressure can make it more anisotropy. The study of this elastic property reveal that this material is brittle under zero and became hard under pressure. No literature reports the experimental values of this property, so we cannot estimate the error between our calculation result and the experimental. Our calculated results are predictive and can serve for a comparison with further work. And thank you for your listening.